the son walks into a casino. He goes to the nearest dealer and asks, "How hot do I gotta be to get 2 protons in a single well?" Einstein didn't believe that the universe could be random. Einstein was also a cringe gambler. He probably lost so much money at a casino that even after experimental evidence showed that particles were inherently uncertain, he would rather believe in a set of underlying deterministic rules that we had yet to understand. Quantum randomness is undeniable at this point, though as most of modern physics, it's pretty inconsequential to day-to-day life. The microscopic changes that it could make are counteracted by the relative macroscopic scale of the human experience. Sure, you could argue for the butterfly effect making some sort of change, but I don't find that particularly compelling. I'm not stealing money from my friends because a chain of infinitesimally small chances made one of them decide to play a hand. I'm stealing money from my friends because I'm a math major specializing in probability, and we decided to play poker while I'm the only one sober. Rather than the butterfly effect, it's much more interesting to look at the minuscule probabilities at maximal scales. House edge for standard table games and casinos is typically 1.5%, and those rake in upwards of billions of dollars in revenue a year. How are they going to make money through such low odds? Millions of events and guys like Einstein. All stars, including our sun, use nuclear fusion to generate energy. By combining two atoms, you create a heavier atom whose mass is slightly lower than the sum of the masses of its parts. This difference in mass corresponds to the amount of energy produced from the fusion reaction. You know, from that funny little equation. Fusing together a kilogram of hydrogen produces approximately 645 terajoules of energy. This is 32 million times that of coal. This makes sense. The core of the sun is approximately 15.7 million degrees Kelvin. It's got to get that energy somewhere. With that in mind, we now take a look at the main reaction our sun uses to generate energy, the proton-proton cycle. First, two protons must fuse, where almost immediately after, one undergoes beta decay. This releases a neutrino and a positron, and turns that diproton into deuterium, an isotope of hydrogen, as up there. Then, that deuterium particle fuses with another proton, creating a helium-3 isotope and releasing a gamma ray. You end up doing those first two reactions twice, where then you fuse two helium-3 particles, which then produce a helium-4 particle and two more protons. Overall, the reaction is 4 protons produces 1 helium-4, 2 positrons, 2 neutrinos, and 2 gamma rays. If we assume we're working with atoms and not with ions, like that shows, the reaction becomes 4 hydrogen to 1 helium-4. Then, considering that, if we ignore the energy of the neutrinos, all other mass must become energy, including the positrons, which will annihilate with electrons. This results in approximately 26.7 mega electron volts of energy released. This may seem like a small amount of energy, but you can't forget that the inputs for that reaction were 4 protons. And the scale that this is done in stars is large enough to make up for it. Our sun fuses about 600 million tons of hydrogen per second. But how does this all actually work? Well, fusion is a direct consequence of the strong force. When two nucleons get close enough, approximately 1 femtometer apart, the strong force glues them together at an unrivaled strength. Through this, and the weak force caused beta decay, the original nucleons can form new atomic nuclei. If this were easy, though, we would have had a functional nuclear fusion reactor a long time ago. To get two positively charged protons close enough for the strong force to take over, you must first overcome the Coulomb force repelling them. To overcome that barrier, the kinetic energy of the particle must be greater than the potential energy of the Coulomb barrier. For the fusion of two hydrogen ions, we can solve for average temperature by equating the average kinetic energy with the potential energy barrier. To overcome the Coulomb barrier, the kinetic energy of the particles in the plasma must be greater than the potential energy of the Coulomb barrier. For the fusion of two hydrogen atoms, we can solve for the average temperature by equating the average kinetic energy with the potential energy barrier. This, then, we can solve for how hot the sun has to be to fuse two protons. First, we set Ek equal to UE, plug in the formulas, and then we solve for T. Setting Z1 equal to Z2 equal to 1, we get 1.1158 times 10 to the 10th, which is a pretty bad number. If you were paying attention earlier, the sun is only 1.5 times 10 to the 7th Kelvin, which is 15 million Kelvin. But doesn't that mean the sun, shouldn't really exist? It doesn't have enough energy to fuse two particles. So then how, you may ask, does the sun exist? And that leads us to our answer, gambling and a bit of quantum mechanics. That's right, baby. God is a gambler, and hot damn are the odds in his favor. If we consider the sun God's casino, his house edge would be approximately 5 times 10 to the negative 18 per second per proton. And you know how he makes up that difference? By having 10 to the 56 reacting protons in the sun, which leads to a whopping 10 to the 38 reactions per second, meaning that the sun burns on. Yo.
Sorry to disturb you. Just to let you know that this building is closed at 10 p.m.
Oh, okay.
Yeah.
Damn.
Odd hydrogen atoms in your area, ready to fuse. Only 1 femtometer away. Click here now.
With gambling in mind, let's now take another look at fusion, this time considering quantum mechanics. Fusion is a quantum tunneling problem, with the Coulomb force presenting as our potential barrier. For any particle collision, the wave function will bounce off the classical turning point, with a bit of the wave function sneaking in to the region where the strong force is dominant. The square of that represents the probability of two particles fusing. From that logic, if we assume that rather than overcoming the total energy of the Coulomb barrier, proton only has to get close enough to another proton to be within 1 de Broglie wavelength, we can revisit our prior derivation. With lambda equal to h over p, we rewrite the kinetic energy with regards to momentum, and we set lambda to the point of closest approach, and we solve. Solving for lambda and then substituting that into r of our prior equation gives us that, and then that. And then, if we solve that, we get a value for t of 9.711 times 10 to the 6, which is basically 1 times 10 to the 7th, which is a value that gives the lowest temperature the core of a star can possibly be.
To sustain itself.
To sustain itself.
Fusion reactors are the fanciest way of boiling water in the land. The two main methods are inertial confinement, where a small hydrogen isotope pellet is heated to temperatures over 100 million degrees Celsius, and magnetic confinement, where plasma is rotated along multiple axes and superheated. The current cutting-edge reactor is ITER, a 23,000-ton reactor, mankind's current peak of global warming technology.